In this video, we'll be learning how to solve ordinary differential equations with Matlab. Let's say we're given a set of governing equations here of a pendulum, and in this pendulum, it is free to spin about axis at A0, and also the pendulum weight is free to spin about the pendulum arm. That is, this boot shape here can spin, as well as this pendulum is allowed to rotate back and forth. This set of governing equations is given as follows. What would be the classifiers for this set of differential equations? Well, we already said differential equations. That is because the angle QA and the angle QB is a second order differential equation. So we have differential equation. Both equations are of a second order. And to understand if it's coupled or uncoupled, we would want to see if QA or QB showed up in more than one set of equations. And in fact, it does. In the top equation, we have QA, that is the angle that the pendulum makes with the vertical axis, and QB, which is the angle that the rotation of this boot makes with respect to the pendulum's axis. And therefore we say that this is a coupled set of equations that govern our baby boot. And we see here that this second derivative, or this first derivative, is squared. So the first derivative of QA. We also have a cosine of QB. There are a lot of nonlinear terms here, so this is a nonlinear differential equation. We can say it's homogeneous if all of the terms include the dependent variables. And in fact, we see there are no terms that have just the independent variable. Therefore, this set of equations is homogeneous. And furthermore, we can say that it is constant coefficients because none of these coefficients vary with respect to time. Often, solving a set of differential equations, such as the baby boot, is either difficult or even impossible to solve explicitly to find a solution for. When this is the case, we can revert to numerical methods to solving ODEs. The numerical methods we cover in this lecture are forward Euler, backwards Euler, Runge-Kutta 2, or the predictor-corrector method, and Runge-Kutta 4, as well as how to use Matlab's ODE functions. Many ODEs that we'd like to solve are what we call initial value problems, or IVPs. That is where we know the initial state of our differential equation, such as temperature, position, velocity, mass, or concentration is known, as well as the governing equation. An example of this that is a classic example is the concentration of a first-order chemical reaction. We say that this is a linear constant coefficient homogeneous first-order governing ODE. That is, the derivative of the concentration with respect to time is equal to negative K, which is a constant coefficient, times the concentration. We probably know this as respect to time. Oftentimes we say this function is given with respect to C and T. The function of this derivative is negative K times the concentration. We might know this initial concentration at T equals 0 seconds. That is the concentration before we start the reaction. We'll call that C naught. What we'd like to solve for is the concentration at a given time, a time greater than T of 0 seconds. Let's derive the forward Euler method for solving ODEs, and specifically an initial value problem ODE, where we have some first order differential equation is equal to some function with respect to t and y given an initial value of y. This is often called explicit Euler method. So we'd like to find this numerical method for y of t for any t greater than 0 up to some t we'd like to know. In order to do this, we'll solve for y at different time steps, where ti plus 1 is just ti plus some change in time, some delta t. We'll do what we did before to discover a numerical method for differentiation and integration, and we'll use a Taylor series to expand the solution about time ti plus 1 around the solution at ti. You can envision here that we would know t of 0, where that is equal to y naught. And if we take a little step, we could solve ti plus 1. So this Taylor's expansion gives us y of ti plus 1 is equal to y of ti plus delta t, the first derivative of y of ti, plus delta t squared over 2 factorial, the second derivative of y, ti, and so forth and so forth. And this is an infinite series. What we know is y of ti, delta t, and the derivative. That is this differential equation right here. What we don't know is y of ti plus 1. That's what we would like to know. These higher order terms here will become the error for our differential method. So the forward Euler method is given as y of ti plus 1 is y of ti plus delta t y prime of ti plus the error of the higher order terms. Now, of course, this is the error of just one step. So we say it's the error of the step is of order delta t squared. That is, that as delta t decreases, it decreases for the step with respect to t squared, or delta t squared. So this is our forward Euler method. It is often equivalently written in the form where we say that the delta t is given as this step h. So oftentimes the notation for delta t or any time step or independent variable step is given as h, and y prime is really the derivative of y with respect to t, and we really say that that's just equal to some function of this ODE with respect to t and y of t. So oftentimes this forward Euler method appears as y of ti plus 1 is equal to y of t plus the time step times the second or the derivatives equation of ti and y of ti. So I'd like to take you through how forward Euler or explicit Euler can be used to solve an initial value problem using Euler's method. That is, we have this equation here, and we'd like to solve for the function y at time 4. We can say that y of time 2 is y of time 1 plus delta t times the derivative of y of t1. So in this case, y of t1 is just 0. And we can step by delta t and this derivative here at y of t equals 0. That gives us y of t2. We can find y of t3 using the forward Euler method, and we have t3 and the delta t, and we can take this derivative of y of t2 and we can add up, and this would give us y of t3. Finally, we can find y of t4, which is just y of t3 right here, plus the delta t times the derivative, which is really just this slope here of the derivative at y of t3. What you can see here is that while we had an initial guess that was pretty close, as we proceeded, our errors of each step added up. So we had an initial small error here, but in this second step, our errors get a little bigger, and in the third step, our errors get bigger still. We have that the order of the error total, so remember, for each step, it's delta t squared, but actually when we add all of these steps up to get the final value of y at t4, we're actually of order delta t. So this is a first order accurate method. While I won't be testing you on it, it is often important to understand the stability of a numerical method for solving ODEs. Consider this model equation that is a first order differential of y with respect to t is equal to lambda y. We say that this is our model equation when lambda is less than 0. We can easily derive an analytical solution for this model equation. By rearranging these terms and integrating both sides, on the left we'll integrate with respect to y of t equals 0 to y of t, and on the right we'll integrate with respect to 0 and t. We can now solve for this integral, and that is the natural log of y over y naught is equal to lambda t. And we can rearrange this in terms of what we'd like to solve for. Y is equal to y naught, the initial value of y, times e raised to the power of lambda t. Now, for our model equation, since lambda is negative, we see that this is an exponentially decreasing function. So it is getting smaller with respect to t. This is our analytical solution. So this is the exact solution. Let's apply the Ford-Euler method to this model equation to see how this stability for this method is. The Ford-Euler method would say that y of ti plus 1 is equal to y of ti plus delta t y prime ti. And what we can do is we can factor out the y of ti, so we have y of ti times 1 plus delta t lambda. We can plug in a few terms here, and what we see is really that this can be y of t3 can be computed as y of t2 times 1 plus delta t lambda. But remember, y of t2 is really just y of t1 plus 1 plus delta t times lambda. So therefore we can say it's y of t1, and it's really this amplification factor here. We can say that that is 1 plus delta t times lambda squared. Or more generally, we can say y of ti plus 1 is y naught, the initial value of y, times 1 plus delta t lambda raised to the power I. We see that this is stable if this absolute value of this term is less than or equal to 1. Therefore, it wouldn't grow with the power of I. Therefore, for real and negative lambdas, we say that this solution is stable if delta t is less than or equal to 2 over lambda, the absolute value of lambda. So this will set the upper bounds on our time step. We cannot make a time step that is bigger than 2 divided by lambda. Otherwise, our method will be unstable. So I'd like to talk how we use this Ford-Euler method with Matlab. So we can write a function called Ford-Euler that accepts a function handle f and an initial time, a final time that we'd like to solve our solution at, and an initial value of y naught, and h, which would be our step size. So the Ford-Euler method is y of ti plus 1 is equal to y of ti plus delta t times really f of ti. So what we can do is set our initial time y of 1, and in many textbooks you'll see this as really I equals 0, but since Matlab is indexed from 1, I'll set y of 1 equal to y naught, or y of t equals 0. And then what we'll do is we'll set a time array where we step from t0 by step size h to t final. The one word of note here is that if this h steps over t final, we won't actually get the solution of t final. We'll get the solution of a time just prior to t final. And then what we'll do is from I equals 1 to length of t minus 1, that is because we've already set this initial time step and we're solving y of ti plus 1. So in this example over here, we wanted to iterate 1, 2, 3 times, and our vector for time was 1, 2, 3, 4. So that would be 2, 2, 4. That was why we're doing length of t minus 1. The Ford-Euler method then would be y of I plus 1 is equal to y of I plus h times f of y of I. In this case, for our equation here, we'll assume that y doesn't vary with t. So now let's use this Ford-Euler method to solve the model equation. So here I have lambda is equal to negative 0.5. Our initial value, since this is an initial value problem for y, will be 1. The function handle for this initial value problem, or this ordinary differential equation, is lambda times y. That's for our model equation. And our initial time will set to 0, and the final time is 10 seconds. Of course, we know the solution to this, so we'd like to plot the analytical solution. So we'll plot t solution as ln space, which is 100 points equally spaced from t0 to t final. And then we'll compute the solution at all times in T solution, and we'll call that Y solution. So let's plot that first section. And what we see is we have this analytical solution for y of t, and it decays exponentially with respect to t as we expected. Now what we can do is give ourselves a time step of 0.25 seconds, and we can pass that to our Euler method function that we just developed, and we can see how this numerical method can solve this differential equation. So let's run this section. And now we see here we have our approximation, our numerical approximation to this ODE, and it's quite close, or at least pretty close, for our numerical method of a time step of h equals to 0.25 seconds. Well, if we increase our time step, remember that the error is related to our delta t squared, that's of each step, and then it's of order delta t for the entire domain. So our error should add up linearly here. So if we compute this one, we'll see that, in fact, yes, we almost do have a linear increase here for each numerical integration. And finally, or actually not finally, we'll step it up again to h equals 1 second. And so now with a cruder time step, we'll see our error is getting larger still. And finally, what we can do is we developed our stability, or the maximum criteria for our delta t was that its maximum value was 2 divided by the absolute value of lambda. So if we add a small amount to this number, we expect the solution should become unstable. So let's go ahead and run it. And we see that our solution, as we take this time step, is varying wildly, and that is what we say it's unstable. So we actually have an unstable, we've taken too large of a time step, and this method is no longer stable for this numerical solution to this ODE. In order to understand the stability of the backwards Euler method, what we can do is apply it to the backward Euler method to our model equation, which we have our analytical solution for. Using the method we just developed, we can say that y of ti plus 1 is equal to y of ti plus delta t lambda y of ti, where lambda y of ti plus 1 is just this f of y right here. We can rearrange this equation, and solving for y of ti plus 1, we can say that it's equal to y of ti times 1 over 1 minus delta t lambda. And we can say more generally that y of ti plus 1 is equal to y of t0 times this amplification factor raised to the ith power. What we see now is, since delta t lambda appears on the bottom and lambda for our model equation is always less than 0, that this is, no matter what term you have, is always going to be less than 1. Therefore, this is going to be stable. So it's not going to be growing exponentially. So along with our equation that's decaying, our numerical solution will be decaying. So this is stable as long as this is less than or equal to 1, which will always be the case for our lambda less than 0. Therefore, we say that this is stable for any time step we take. So while it is computationally more difficult to do implicit Euler, it's actually stable for all delta t. So if you, for some reason, need to take a large time step for your numerical integration, a good choice is backwards Euler. So what I'd like to do now is use this method in Matlab. So let's apply it again, once again, to our model equation for lambda. And in this case, just like we did for the forward Euler method, I'll let lambda equal to negative 0.5. And then down here, what I'm going to implement is our implicit method. So that's where we solve for y of ti in each step. So what I'll do is I'll set my time step equal to 0.25 seconds. I'll set my t as equal to t T naught step by delta H to T final, and then I'll set y1 equal to y naught. In this case, I'm not going to do a generic function because I actually have to solve it each time, so it's kind of hard to know a priori what the solution to that is. Now, of course, here we can solve this for our differential equation, and it's really just 1 over 1 minus h times lambda times yi. So that's actually the solution to this if I were to plug in this f of t and yi as lambda t. Okay, so what that's going to do here is that's going to solve this with a backwards method. So I'll go ahead and run this first section, and then I'll run this second section, and I'll show you this numerical solution. So what we see here is this backward method with a time step of 0.25 quite accurately approximates the analytical solution. I can increase this and step size to 0.5, and we'll see here that our error is increasing linearly. And I can increase it to a step size of 1, so that's going to increase h and to 1 second. So I'll run this section, and my error is greater still. But what's really of interest here is if I take quite a large time step, so a time step of 4.2 seconds. Now remember, this would have given us an unstable solution for our forward Euler method. However, we said that our backward Euler, we derived it was stable for all delta t. And so if I run this section, I expect it to be stable, and in fact it is. So the reason I didn't get the solution here at 10 is because I stepped forward by h, and I can't step by 4.2 from 0 to 10 seconds. So I didn't actually get the solution at 10 seconds. So I can't take a uniform step size, which is actually one requirement for these simple methods of backward Euler and forward Euler method. But I do have a stable solution, so I'm not wildly growing out of control as I grow my delta H or delta T. While forward Euler and backward Euler are both effective methods at numerical integration, they're quite inaccurate. One way to increase the accuracy of these methods is the Runge-Kutta method. And what that does, and there are multiple Runge-Kutta methods, but in general, they all increase accuracy and stability with additional computations at intermediate points between ti and ti plus 1. The easiest example to understand is Runge-Kutta 2, that is oftentimes called a predictor-corrector method. In this method, what we do is the first step, we predict what the value of y of ti plus 1 is with forward Euler. So this is still just our forward Euler method. So we call this y tilde. That is the predicted value of y at ti plus 1. So we use our forward Euler method to predict this. Where here I'm saying this is h is delta t, and y dot, which is the time derivative of y. So this notation here, y dot, it's equivalent to saying this is the derivative of y with respect to t, is equal to f of t and y of t. Okay, what we can do in our second step, and this is why this is called RK2, Runge-Kutta 2, is correct our prediction for y of ti plus 1 using this differential equation evaluated at ti plus 1 plus our predicted value of ti plus 1. So here we have a graph showing that the tangent line at x of n, or really of ti, is here. So this is the predicted value of y. And then the slope at this predicted value of y, so this would be the second one, that's the prediction here. And what we can do is, since these two predictions, they are different, what we can do is take the average of those. So that's what the corrected step is. So we say our corrected prediction of y of ti plus 1 is equal to y of ti plus our step times the average of those two slopes. And this gives us Runge-Kutta 2. And the error for this is of order for the total entire step from t of 0 to t final, so the addition of all of them. So this isn't just for one step, it's the total error is delta t squared. So this is a more accurate method than forward Euler or backward Euler. Unfortunately, the stability of this is the same as the stability for forward Euler. The Runge-Kutta fourth order method, or oftentimes referred to as RK4, takes 3 steps in between t of 0 or ti and ti plus 1, and does 2 function evaluations at t of I plus the delta t over 2. So the first step, just like RK2, is still forward Euler. So we predict the value of, we call it K1 times h of f of ti and y of ti. So this is just forward Euler. And then the second step, we calculate a new value for k. We call this our K2, and that is this derivative of a K2. So really it's h times f of ti plus h over 2. So this is half of the time step, and this y value, ti, and then plus k1 over 2. So we plug in our k here. So this is like a RK2 right now. So this is like the predicted value of y. So we're calculating this of this new time step and this predicted value of y of ti plus this forward Euler. And then what we do here is we do our third step, and now we do f of ti plus h over 2, so the same time step, but now we're adding the k2 over 2. And finally, what we have is k4 times h f of ti and y of ti plus k3. So the final method adds up all of these, and we assign weights. So what this you'll see here is we assign more weight, so it's 2 times the Kutta evaluations at this half time step. So we weight those more heavily on this, but then we're taking this first forward Euler and the last one, and we're averaging all of those, weighting these first 2 more heavily, and that gives us an accurate prediction of this function at y of ti plus 1. The error of this is actually of order t to the 4th. So we've got a huge increase in our error, and also our stability is increased over forward Euler. So RK4 is a very good numerical method for solving ODEs. So I'd like to show you how to implement Runge-Kutta 4 in Matlab. So in order to do this, we'll say y1 is equal to y0. That's the initial value passed in here. And note, and actually with all of these, we're assuming these function handles do not vary with t. And if that was the case, I would need a t term here when I evaluate this function. But we'll let t vary from t0 to t final, and we'll step by our given step size that the user gives this function. The first step we will do is calculate K1 using forward Euler. We'll calculate K2, we'll calculate K3, we'll calculate K4, and then in the final step here we'll say that the y of I plus 1 is y of I plus the weighted average of these intermediate steps of this function evaluation. Okay, so let's take a look at this example, and just as before, we'll compare this with our analytical solution of the model equation. So if we do Runge-Kutta, remember this was 4th order accurate, so when we evaluate this time step of 0.25, we expect it should be much more accurate than our other methods such as forward Euler and backward Euler. So we run this section and we see that is indeed true. So here on this plot, it's actually tracking right along with our analytical solution. And even if we step our time step up, we still get a very good accuracy. That's because we're doing a lot of function evaluation. So even though we're taking a larger time step here, we've done a lot of function evaluations in between. And I continue to step my time step up, and we still have quite an accurate solution, and I'll go ahead and step it up to 4. Now remember that when I said h is equal to 4, that was right on the limit of stability for our forward Euler method, and actually for RK2. So if I run this, you'll see that while the error is large, because we have quite a large time step, I'm actually not unstable. So I'm still a stable method. And remember, the stability here is actually increased to 2.79 divided by the absolute value of lambda. So if I evaluate this, what I would expect is now my solution for RK4 to become unstable. And in fact, we do see that is the case. So now we have an unstable solution. So you can't go with too large of a time step that is bound by 2.79 over the absolute value of lambda. So that is our limit of stability for RK4. So what I'd like to do now is compare all of the methods all the numerical methods that we've talked about so far. So that's our forward Euler, our backward Euler, our Runge-Kutta 2, and our Runge-Kutta 4, and let's compare these all at a step size of h is equal to 1 second, and let's compare that to the analytical solution. So here I've just evaluated all 4 methods, and I'm going to plot them all. So if I run this section, what you see, and I'm actually also running ODE 45, so we'll talk about that next, but that's the numerical method which uses RK45. That is a Runge-Kutta method also, and that is Matlab's numerical method for solving ODEs. What you can see here is our accuracy of forward Euler is the worst. It's a little bit improved with backward Euler, a lot improved. So remember that was, so these two methods were of order of delta t, and this is delta t squared for RK2, and RK4 is of order delta t to the 4th, so a significantly increased accuracy. So even though we have a large time step, we have a very good evaluation of our numerical method for this ODE. And you can hardly tell the difference between RK4. So if I go ahead and zoom here, you can't even see RK4. That's because it's right on our numerical method from Matlab, which uses a RK45, so it's right on top of it. So it's slightly different, and actually, in fact, we won't even be able to probe this difference until we see a large time step. So what I'm going to do here is let's take a much larger time step, so a time step of 4.2. So we expect that forward Euler and RK2 should be unstable. RK4 should be stable but have an error, and we'll see how it compares to our RK45, which is ODE 4.5. It's 4.5 because it's a Runge-Kutta 4.5 method. So let's run this section. And we see, as expected, our forward Euler and our Runge-Kutta methods were wildly unstable. But actually now we've kind of probed the difference here. Our Runge-Kutta 4 is not that accurate, while our ODE 45 is still very accurate. So it's still an accurate numerical method.